Okay, I want to move on now to discuss some specific examples of synthetic transformations in between various carboxylic acid derivatives and what some allowed versus non-allowed reactions are. You should keep in mind that reactivity ladder. That will be quite important for understanding why we do the reactions that we do and the order in which we perform these syntheses. So one key transformation is being able to go from a carboxylic acid to an acyl chloride, or to be able to transcend the reactivity ladder. And this is normally not allowed. You cannot add sodium chloride to this and it will not make a chloride, right? We know the carboxylic acid is more stable. We'll talk about how we achieve that in a second, but the relevance to this is that you can take any carboxylic acid derivative, and as long as you add water, maybe with base or with acid, perhaps an equivalent of those, or perhaps very high temperature, any carboxylic acid derivative can be taken to a carboxylic acid. Once you get there, there's a key synthetic step with thionyl chloride, and oftentimes you'll have a base in solution to mop up an acidic product. Thionyl chloride will irreversibly take you up the ladder to the chloride. This is very important. So some side products you make here are the pyridinium ion, that mops up the extra proton here. Additionally, you make sulfur dioxide, and that turns out to be a gas. And it's the formation of this gas and its liberation from the solution that depletes the products, keeps Q small, and drives the reaction to completion. That's a mechanism that you may or may not need to know. It's widely available on the internet in many sources. For the interest of time, I just want to think about how we use this reaction in synthesis. So, let's do an example. We start with a nitrile, and there are not many reactions that nitriles can undergo. It's extraordinarily stable. Let's say that we turn that into an anhydride. And this has gone up the energy ladder. So there is no one-step procedure that you can use. However, we know the anhydride can be made from the more reactive chloride. You could achieve this by using acetate as the nucleophile, right? Or acetic acid. And that would be a product favored step. Additionally, the chloride can be made from the carboxylic acid via thionyl chloride. And once you get to the carboxylic acid, then you are golden. Any carboxylic acid derivative can be made from a carboxylic acid in 2 steps. The final procedure is simply to hydrolyze. We know that nitriles can be turned into carboxylic acids with excess water, strong acid, 1 full equivalent. It's acid mediated and irreversible, and lots of heat. And that's the 10-step mechanism that we saw in one of the last videos. So this is an example of how you can go from any carboxylic acid to another, generally within 3 steps, assuming there are no carbon-carbon bonds that are being formed. You get to the acid, turn it into a chloride, and then go down the ladder anywhere you'd like. So let's do another example. So the starting material here will be a benzaldehyde derivative. The meta-bromo. And the desired product is a methyl ester. This reaction cannot be done in one step. There are many things we must consider. First of all, what I notice is that we have formed a new carbon-carbon bond. This carbon-halogen bond here has been turned into a carbon-carbon bond. And generally, when you see a carbon halide bond that is reactive, you can turn that carbon halide bond into an organometallic. Like a Grignard or an organolithium. And that will allow us to add some carbon electrophile to give the product. So let's think about what that carbon electrophile needs to be. If you think about ester synthesis and the direct intermediate that existed before the ester, one good option would be the chloride. Chlorides are highly electrophilic and can be turned into esters readily. You could do this with methanol and some base like pyridine that will deprotonate methanol. You could also use triethylamine. You could also do it under basic conditions with sodium methoxide. That would work as well. It's a better nucleophile, and no base would be required. And we know the chloride is a nice intermediate to have because he can be made efficiently from the carboxylic acid. And now we see we need to make a carboxylic acid derivative from a carboxylic acid, which can be made from a bromide. So when you do this one carbon elongation, this has one more carbon than the starting material. And you get a carboxylic acid or one of its derivatives in the products, you should think carbon dioxide. So I'm going to turn this into a carbon nucleophile that can then react with carbon dioxide. However, there's a problem. If I make a carbon metal bond here, that is going to be very nucleophilic and could begin to react with aldehyde electrophiles in solution. So before I make any organometallic, let's keep the bromide for now, I need to protect this aldehyde to prevent it from reacting in basic solution. You make it into an acetal. And acetals are unstable in acid. They will reverse and fall apart. But in basic solution, they will not react. Any alcohol in excess, like ethanol or methanol, is fine, with a catalytic amount of strong acid. You could, of course, use a diol in one equivalent, like ethylene glycol. You could use either of those. Next, we now have a protected aldehyde, and we can turn the carbon into a carbon metal bond. I'll make a Grignard, but organolithium reacts in an analogous manner. And so now, to get to the Grignard, you add magnesium in some ether solvent like THF or diethyl ether, some anhydrous solvent that is not acidic, it is not protic, and it will not quench your strong base, your Grignard reagent. We want this to be a nucleophile that is saved for when carbon dioxide is added. We don't want there to be any protons in this solution. Otherwise, they would just react with the carbon. Addition of carbon dioxide, which is in the +4 oxidation state, will give a new carbon-carbon bond with a carboxylic acid that's in the +3 oxidation state. Nucleophilic addition here is followed by, so this is step 1. A little bit later, you would add hydronium to protonate and make the carboxylic acid. From then, you add thionyl chloride. And then esterify it. Another simpler way would be after carbon dioxide, you would have an O-, and that O- could just react with a methyl electrophile, like methyl bromide. So that would be equally correct. Instead of doing the acid workup, just add a methyl group there. It would go in place of the hydrogen. That would be via an SN2 reaction. So, I want to talk about one more aspect of some of these carboxylic acid derivative interconversions and the issue of equivalency. And this is going to be focusing around the chloride, the ester, and the anhydride. Specifically, I'm most concerned with adding amine nucleophiles, where amines are moderate bases. And because they are basic, they will react with any acid in solution. So let's just use the same amine for each of these. Let's use ethylamine. But any primary or secondary amine would follow the same trend. With the chloride, it'll displace the leaving group. You make an amine, and the side product here is HCl. You get the same secondary amide for each of these. Good nucleophile attacks. A proton transfer may or may not occur. Leaving group leaves. And you deprotonate the nitrogen to get the amide. They all make a side product. The conjugate acid of the leaving group is the side product. Here we get methanol. And keep in mind the various pKa's of these conjugate acids. Very strong acid, a moderate acid, and a very weak acid. So, if you are building up an acid in solution where you have an amine trying to attack, not all of these molecules attack at once. Some of them are still stuck at the starting line, waiting to go. They're waiting for their turn. And as you start to make some amide, for every equivalent of amide you make one equivalent of acid. And we know that acid base is fast. And so what will happen is you'll end up protonating any of your amine that has not undergone addition to the carbonyl yet. It'll deprotonate acetic acid. And the pKa of the ethyl ammonium ion is around, let's say 10, but I think it's between 10 and 11. So what we see here is the equilibrium constant for this reaction with HCl is super, super product favored, 10 to the 17. And it's still quite large. it's 100,000 to 1 for the carboxylic acid. So those are going to start ruining and fully, irreversibly protonating your amine. And now the amine cannot serve as a nucleophile. So it's irreversibly protonated. So what that means is you have to add 2 equivalents of the amine when you have a very electrophilic with a great weak base leaving group starting material. If you have a chloride or an anhydride, they are so reactive because they have great leaving groups that are weak bases, which means their conjugate acids formed here are relatively acidic. And that side reaction, the acid-base reaction that starts to occur, does not stop. It just happens immediately. And it's fast and it's irreversible. Or at least has a very large equilibrium constant. Which means you have to have one equivalent of amine to act as the nucleophile and give the amide. The other equivalent of amine must be used to make the conjugate acid, or to mop up the side product. With aminolysis, which is this reaction below with the ester is much less reactive and has a worse leaving group. The leaving group here, methoxide is more basic, and methanol is not very acidic. So this means that this is a weak acid, and that will not protonate the amine. Or at least it won't do so to a large equilibrium extent. So you only have to have one equivalent of amine with an ester. Now, another option for the chloride and the anhydride is to add one equivalent of amine and one base, like pyridine or triethylamine. That's true for these two. These abide by the same rules. You either need 2 equivalents of your amine and you get 1 equivalent of product, or you need an equivalent of amine, an equivalent of pyridine or triethylamine base to mop up that acidic side product.